Hello chemists, this is Ms. Placino and you are watching Screencast 13.2 on redox half reactions. In today's lesson we're going to talk about how redox reactions are expressed. Don't stress out, you've actually seen redox reactions before, you just did not know they were redox reactions. For example, this is a redox reaction. Now before today's lesson you would most likely classify this as a single replacement or single displacement reaction, one and the same. So you might be wondering, well, what makes this a redox reaction? First thing you want to do is go through and assign oxidation states or oxidation numbers to each element, both on the reactants and the product side. So let's do that together. Zinc is uncombined. We know the uncombined elements are going to have an oxidation state of 0. Copper is a transition metal. It could be +1 or +2, so let's come back to that. Chlorine, in an ionic compound, chlorine is going to turn into chloride with a charge of -1. If I've got two chloride ions, that means the oxidation state of copper must be +2. We'll come on over to the product side. Let's take care of the easy one first. Copper is uncombined, so it has an oxidation number of 0. Chloride is still going to be -1. And zinc is going to be +2. So we've gone through and taken care of step 1. We've got oxidation states to each element in the reaction. If you're not sure how to assign oxidation numbers, you should really go back to the previous lesson. What makes something a redox reaction is that over the course of the reaction, oxidation states for two elements, or potentially two elements, have changed. So if you look, we've got zinc going from an oxidation state of 0 to +2, and we've got copper going from +2 down to 0. We know that the loss of electrons is oxidation, and we know that the gain of electrons is reduction. So if we take a look at what we've got as far as changes in oxidation states, let's see if we can figure out whether zinc or copper has been oxidized. Now we'll start with zinc. So initially zinc has an oxidation number of 0, and at the end of the reaction zinc has an oxidation number of +2. So in order to go from 0 to +2, zinc must have lost 2 electrons. That sounds like oxidation. I'm just going to put that over here. In this case, zinc has been oxidized. Now, by default, copper must be reduced. Oxidation and reduction reactions always come in pairs, hence redox, reduction, oxidation. But let's just double check and make sure. So copper started off with an oxidation state of +2. At the end of the reaction, it has an oxidation state of 0. In order to go from a +2 to a 0, copper must have gained 2 electrons. So in this case, copper has been reduced. So we know this classifies as a redox reaction. What we're going to be able to do is write half reactions. So I'm just going to quickly put up the oxidation states again for the elements that have changed. I'm going to leave chlorine alone because it's kind of more of a spectator ion than anything else in this reaction. So we need to represent the oxidation of zinc. And if we think about really what happens over the course of the reaction, zinc is going to lose 2 electrons to become Zn2+. We're going to represent that in a different way. Instead of showing the 2 electrons over the arrow, we're going to put it in on the product side. Let me erase this to avoid confusion. So we start off with zinc. We end up with a zinc ion, Zn2+. I have a charge of 0 on the reactant side. I have a charge of +2 on the product side. So I need to balance for charge. That's where the electrons come in. In half reactions, we're going to be using electrons to make sure that there has been no change in charge as we move from reactants to products. So the only way to keep this neutral, this Zn2+, is to add 2 electrons. And this makes sense when you think about it. Oxidation is a loss of electrons, so electrons are being lost from zinc atoms, so they turn into zinc ions. The reduction reaction. All right, we go from copper 2+ to copper 0. Over the course of the reaction, copper 2+ ions gain 2 electrons. Again, we need to make sure charges are balanced. We start off with Cu2+. We end up with Cu with an oxidation state of 0. So to balance the charge, we've got to make sure that we add those 2 electrons in. In any oxidation half reaction, your electrons are going to be products in reduction half reactions, electrons are always reactants. So I can kind of remember that by pairing up the R in reduction and the R in reactants, just to hopefully prevent you from making any careless mistakes. All right, the last thing that I'd like to talk about before we get into some practice problems are oxidizing agents and reducing agents. And again, whoops, made a mistake. Let's just put these oxidation numbers up there quickly. The oxidizing agent is the species in a reaction that is reduced. This often causes problems for new chemists. It's a little misleading. We're talking about oxidizing. Wait, this is the substance that gets reduced. Well, really in the definition, an oxidizing agent is the substance that is allowing oxidation to occur. In order to allow oxidation to occur, that substance must be reduced. Reducing agent. This is the species in a reaction that is oxidized. So again, we're talking about a reducing agent. This is a chemical or a substance, whatever you'd like to think of it, in the reaction that is allowing reduction to occur. Therefore, if it's allowing reduction to occur, it must get oxidized. Actually a couple of things to point out. Oxidizing agents and reducing agents, they're always going to be on the reactant side. We don't really pay attention to our products. I'm just going to cross those out for the time being. The other thing to make note of is that it's the entire substance that is the oxidizing or reducing agent, not just the element by itself. So for example, in this problem, we know that the Cu2 plus ion is reduced. Therefore, copper chloride, more specifically copper 2 chloride, is our oxidizing agent. Not just the Cu, it's the whole substance. The reducing agent for this reaction is going to be the substance that gets oxidized. All right, zinc is oxidized. Zinc is by itself, so we don't have to worry about making it a compound. Zinc is our reducing agent. So those are really the couple of things we've got to keep track of from this lesson. First of all, we need to be able to look at a balanced chemical equation. We have to assign oxidation numbers to every element present on both sides of the reaction. We've got to figure out which element has been oxidized and which has been reduced. And finally, we need to assign or determine which is the oxidizing and reducing agents. So let's go ahead and work on a practice problem. Okay, in your notes, you've got this reaction. You've got magnesium reacting with chromium 3 bromide to form magnesium bromide and chromium. So just for old time's sake, let's go through and balance. If I take a look, it's the bromines that are not balanced. I must need 2 and 3. That'll balance those up with a total of 6 bromide ions on both sides. So I'm going to need 3 magnesiums, and I'm also going to need 2 chromiums. Okay, so let's get into the stuff that we've talked about today. We know the first part is assigning an oxidation number to every element present on both sides of the equation. Magnesium by itself, so it gets to 0. Chromium is a transition metal. It's got many different possible charges. Bromine, when it forms an ion, the bromide ion always has a charge of -1. Since I had 3 bromide ions present, that means that chromium must have a charge of +3. If I come over to the product side, magnesium is a group 2 metal. Group 2 metals always have a charge of +2. The bromide ion, again, remains at -1, and chromium atoms are uncombined, so they'll get an oxidation state of 0. Okay, as you look at the reactants and you look at the products, hopefully it's very clear to see that elements are changing oxidation states. Magnesium's going from 0 to +2, chromium's going from +3 to 0. So we know chromium and magnesium are the two substances that are really being oxidized and reduced. So let's figure out which is which. Oxidation, magnesium goes from 0 to +2. It must have lost 2 electrons. Therefore, magnesium has been oxidized. Chromium, by default now, must be reduced, but let's just make sure that's the case. Chromium was 3+. Now it is 0. Okay, chromium had to gain 3 electrons to experience that change in oxidation numbers. The oxidation half reaction. All right, so I start off with magnesium. And if you want to put the 0 up here, you can. It's not necessary. It's implied if it's just an element. And I end up with magnesium 2+. Now I'm not balanced for charge. I've got 0 over on the reactant side and +2 on the products. The only way to get that balanced is to use electrons. If I put 2 electrons over on the product side, now I'm balanced for both mass and charge. Let's take a look at the reduction reaction. We start off with chromium 3+. As the reaction progresses, we make chromium, I'll put the 0 up there again. We're balanced for mass, 1 chromium on each side. We are not balanced for charge. We've got +3 on the reactants, 0 on the products. So in order to balance that out, let's add 3 electrons to our reactant side. Now we've got 0 for a charge on both sides of the equation. Last but not least, we have the oxidizing and reducing agents. The oxidizing agent is the substance that gets reduced. Okay, well, chromium is reduced, but it's not just chromium. Remember, it's the whole compound. So CrBr3 is my oxidizing agent. The reducing agent contains the element that gets oxidized. Well, magnesium gets oxidized. It's all by itself. So my reducing agent in this reaction is magnesium. That's all there is to it. We've got another practice problem over here. Pause the video, try this out. We'll get the answers up and quickly review it. All right, check your answers against what we got on the screen. So balance with 1, 2, 2, 1 for coefficients. I've assigned my oxidation states. Looks like fluorine is undergoing oxidation. Goes from -1 to 0. That's the loss of electrons. Iodine, on the other hand, is getting reduced. It starts off at 0, ends up with an oxidation number of -1. I've written the oxidation and reduction half reactions in 2 different ways. The way in red is technically incorrect, but it is something that I will accept, especially very early on. We know that fluorine and iodine are diatomics, and the way they're written in the equation in red, they're represented as monatomic atoms, which really isn't accurate. And green is a better way to represent it. I know that I have F2 as a product and I2 as a reactant in my oxidation and reduction half reactions respectively, so we can just double the number of ions we have, double the number of electrons that we both produce in oxidation and gain in reduction, and that's a much better way to write it. So if you wrote it like I did in the red, no problem, you've got the general concept down. If you were able to jump ahead and do what I did, I guess I just circled it in blue, but in the green writing, that's excellent. That's really the proper way to write it. Finally, oxidizing agent gets reduced. Well, iodine was reduced, so the substance containing iodine is the oxidizing agent. Oh, that's just I2. Great. That means Kf must be the reducing agent because it contains the substance that gets oxidized, or the element, I should say, that gets oxidized. In this case, fluorine. Remember to write the whole thing. All right, that wraps it up for this lesson. As always, do the practice problems. Make sure you're feeling comfortable with this concept, as we will build on it in future lessons. Thanks a lot for tuning in, and I hope you found this helpful.